Today we're going to talk about two things. First, derive two equations, and then we'll talk about solving a physics problem. Now, we aren't going to derive many equations in our class, but I like you to see that equations come from somewhere, and they're just not coming from thin air. So on the board, we have two of the different things we've talked about. We know that acceleration is equal to change in velocity over time. That's our slope formula. And that our average velocity is equal to distance over time. That's our other slope formula. So what we're going to do is we're going to kind of manipulate these to come up with two more usable forms of these equations. Let's start with this first one, okay? Change in velocity. The change in velocity can also be written as acceleration equals v final minus v initial all over time. All I've done here is I've changed change in velocity to final minus initial. We're often going to use subscripts like this. If you ever have a question about what a subscript means, please ask. Now this is almost done. All we're going to do is rearrange some of this to make it slightly more usable. I'm going to move the t over, meaning AT will equal VF minus VI. And I'm going to move our initial velocity over. So I will see that initial velocity plus acceleration times time equals my final velocity. This is our very first physics equation, monumental moment. I like to refer to this as the Model T, the first car, first physics equation, plus it uses this simple version of t, which can be helpful to us for remembering. Again, remember, VI stands for initial velocity plus acceleration, which is, or A, times time equaling final velocity. Okay? Velocities are measured in meters per second. This is also measured in meters per second. Acceleration would be measured in meters per second squared, and time is measured in seconds. Not too bad to begin. All right, now we're going to take a look at our second equation. Average velocity equals d over t. Now, I'm going to play around with that word average, okay? The average of something is taking two of the values, or multiple values, adding them up and dividing by how many there are. We are going to use the initial velocity and the final velocity and divide by 2. To represent our average velocity, since we're going to have a consistent change in velocity with our acceleration, this is going to be okay to deal with. Okay, now, instead of using that many different unknown values, I'm going to now take what we just solved for. We know that VF is equal to VI plus AT, and substitute that into my equation. So VF, as we found down here, is the same thing as VI plus AT, that I just subbed in for my VF, plus VI all over 2 equals D over T. I'm going to move this down just a little bit. Sorry, our board got a little cramped. Now I'm going to combine like terms and move things around. So I got 2 VI's, or initial velocities, and they both have a denominator of 2, plus an acceleration times time with a denominator of 2 equal to distance over time. Now hang in there, we're almost done. Now what I'm going to take a look at is I'm going to get rid of this 2 over 2, it's the same thing as 1, and I'm going to move my time over, meaning I'm going to have to multiply both of these terms by time. So I'm going to be left with initial velocity times time plus 1/2 times acceleration times time again, or time squared equals d. This, my friends, is my second equation. This is an equation that we call the bulldozer. It just kind of is a lot of plug and chug and just plows through all of our different problems. How it got the bulldozer name, I'm not really sure. But it's a lot easier to have kind of a name to talk about these problems with. So this is our bulldozer. Again, VI is going to stand for our initial velocity. That's measured in meters per second. Time, or T, is measured in seconds. A is going to represent acceleration in meters per second squared. T is going to represent time again. And D is going to represent the displacement, meaning this could be a positive or negative value. It simply tells you how far from that starting position you have moved. Not necessarily if you went up and back, but looking at your starting point and your ending point, how much distance is between those two, okay? Make sure that you have these two equations in your notes. Make sure you can identify what all of the variables stand for and what all of the variables are measured in. If you need to hit pause, go back and take a little bit more time to get that down, please do so now. Because now what we're going to do is we're going to start solving some problems using these two equations. Before we start solving problems, I like to go through my list of steps. This list of steps is something that I think you can use in any physics problem throughout the course of the year. My first biggest thing is always draw a picture. A picture is going to give you a better feel for what's actually happening. It lets you know which way objects are moving, and it gives you kind of a sense of where everything is. List your known values. We're going to see in this next problem that there are some known values that we know but aren't explicitly told to us. List out unknown values and figure out which one you're looking for. Once you know what you're looking for and what you have, it's going to be much easier to determine which equation you are going to want to choose. Then, once you've chosen an equation, plug in your known values and figure out what your unknown value is. Check your answer, your units, and your sign. You want to make sure that your answer makes sense. And also that your sign makes sense. That if it's got a positive velocity, it's moving up. If it's got a negative velocity, it's moving down. And finally, record your answer. So, let's put these steps in action. Over here, I have a problem. It says that from a height of 5 feet 7 inches, approximately my height here, I dropped my keys. Exciting, I know. I want to know how long does it take for these keys to fall. So, let's draw a picture. Okay, I'm standing here, my stick figure self. I have my keys at my head level. Clearly, I have an awesomely long arm. And the keys are going to fall for a distance and hit the ground. Not too bad. This just, again, puts things into perspective. The keys are falling downward. Okay, so let's list what we know. Well, since we know how high this is starting, and the fact that it's hitting the ground, we know what the distance is. Displacement is going to equal 1.7 meters. Now, these keys are falling downwards, so they're starting up here, they're going to 0. So this is actually going to be a negative displacement, okay, because we would take our final position, 0, subtract our initial position, 1.7 meters, to get a negative 1.7 meters. And well, that's all it really tells us right now. When we look at our equations, that's not going to be enough to really help us. If we look deeply, though, we can find out some more stuff. First off, they're falling. Whenever something falls, it always is going to fall at a constant rate. You know what that rate is. It's gravity. So, we know, constant rate of acceleration that is, that it's falling at a constant rate of acceleration of 9.8 meters per second squared, and it's pulling it faster and faster in the downward direction. So it's negative, okay? Also, I dropped the keys. What is the very starting velocity here? split second it leaves my fingers, it really didn't start with any velocity. It wasn't until gravity started pulling on it that it got velocity. So we can say that my starting velocity, my initial velocity, is equal to 0. Now, we want to figure out how long it takes for them to fall. It's asking for how much time does it take to fall. This is my unknown value. That's what I'm searching for. So if I take a look here, I know distance, acceleration, and initial velocity. I'm looking for time. So if I take a look at this equation, well, I know initial velocity, I know acceleration, I don't know time, and I don't know final velocity. This is not the equation I want to use. If we take a look at the bulldozer, however, I know initial velocity, I want to solve for time. I know acceleration, I want to solve for time, same thing, and I know my distance. Since time is the only variable that I do not know, the bulldozer is going to help. So I choose this equation, I'm going to write it out. D equals VIT plus 1/2 AT squared. And then I'm going to plug in my actual values. So I'm going to say negative 1.7 meters equals 0 meters per second times time plus 1/2 times negative 9.8 meters per second squared times time squared. Okay? This whole chunk is going to disappear. 0 times anything is simply 0. I would be left with negative 1.7 meters equals negative 4.9 meters per second squared times time squared. Simply going to divide my negative 1.7 by negative 4.9 and take the square root. Take a moment and try that on your calculator. When you do, you should end up with a time equaling approximately 0.589 seconds. First, we have a positive time. That is definitely good. Secondly, let's check. Make sure this number makes sense. As I drop my keys, I'm going to count 1/1000, about the time of a second, and we'll see if we're about right. Our mark, get set, 1/1000. And it hit before I finished. It was most of the way through, little over half, and we got to a pretty decent number. We can't be super exact, but a number that's less than 1 makes sense in this situation. The next part of the problem asks us to solve for the final velocity when they hit the ground, or their velocity when they hit the ground. When I go over there to solve, I'm going to keep all of this same known information, except now I also know the time. I know that time is 0.589 seconds. Since I know that the time is that, I can now say I want to solve for final velocity and go from there. Now, when I take a look at my two equations, the bulldozer does not make sense to use. Final velocity is not even a part of that equation, so it wouldn't help me to find that variable. When I take a look at the Model T, I know my initial velocity, I know my acceleration, I know my time, and I'm looking for final velocity. This is a perfect fit. So if I write this out here, we end up with final velocity equals VI plus AT, and solving for final velocity, initial velocity is 0 meters per second plus negative 9.8 meters per second squared times time. Oh, and my time is what we just solved for. It's 0.589 seconds. This is a pretty easy problem to plug into your calculator. 0 is 0, and negative 9.8 times 0.589 is going to give you an answer that says VF is equal to negative 5.7 meters per second. Now, why is the final velocity negative? Ask yourself these questions. Well, Which way are the keys moving right before they hit the ground? They're moving down, which is our negative direction, so that works out really well. Okay? We also, in this case, can't really take a look at the number. It's hard for us to gauge velocity. If you want to put it in perspective, this is approximately equal to 12.75 miles per hour, which is pretty impressive when you think about the fact that gravity can accelerate things ever so quickly. This is the basics of how to solve a physics problem and our first two equations. Pretty soon we're going to learn about a new equation called the Porsche, but until then, let's start working with these and we'll kind of get some of this information solidified. Have a great night.